do that. This question actually is from Portable TA. So if you are following the advice that I gave at the beginning of the session and you are making use of the fact that our exam breaks exactly match the review problem set, so you are using the Portable TA to review how well you're doing. That particular question, you should be able to find it either in chapter 12 or probably chapter 13. I think I remember getting this particular question from the Portable TA. So I like this question because it makes you think through the conservation of energy and conservation of momentum questions. So, so I'll just point out a few key things that you need to be realizing as you are working through this question. So it says a small frictionless block slides rightward at some initial speed. Slide, it begins to slide up the ramp of mass. Trying to highlight all the quantities given. And then it says the ramp begins to slide to the right. Hopefully that makes an intuitive sense that as this block is moving up the ramp, it's going to slow down, and it slows down because of the force that the ramp is applying, or that's one of the reasons it's slowing down. So there's, so as the block is kind of on the ramp, there's a force on normal force on it from the ramp. That's and then you should recognize that there's a reaction force on the ramp, which is going to, I'm not drawing this in a very good directional wise way. There's a reaction force on the ramp, which should be pushing the ramp to the right. And also, since this small block will be slowing down, in order for total momentum to be conserved, the ramp should be moving to the right, so that the momentum is conserved. And it says, okay, so the reason I'm pointing this out is this is one of the skills that people who are in physics 4A, I see it neglected the most often. Too many students just try to work through this class by memorizing formulas. And I'll tell you that you are setting up yourself to get tricked by some of the more difficult questions when you do it that way. The most useful skill you need to develop that should be helpful to you is the visualization, is the physical intuition. So as you are reading the description of the question, you should visualize what's happening. You should make sure that what the question says is happening makes sense from your physical intuition. And if not, you should be developing that intuition. Okay, so it asks, what maximum height h does the mass m reach before it begins to slide down the ramp? And the first time you see it, it can be a very difficult question to answer. And this is, once again, where the visualization skill is helpful. So let me kind of try to point out what I mean by that. So you have the ramp, and you have the mass m, and you are looking at it. So, at least the starting place is that you're thinking, all right, so I have this, which is sliding up the ramp. And then I have an intuitive sense that as it slides up, it's going to slow down. So at some point, it'll reach the highest height and then begin to slide down. Then what information can I use to kind of get some sense of what's going on at this maximum height? Oops. What this maximum height h? And this is not something that you would see written down in some formula or in some rule of thumb, but this is what you might realize as you are visualizing this setup, that at this highest height h, that this block mass m, it's not going to be moving relative to the ramp. So so because the ramp started moving to the moving to right, the moment it was sliding up, they will be moving, this whole thing as a whole will be moving together at some speed v. So don't ignore that. But at this highest height, because it's just stopped going up the ramp and it's now about to go down. So you can kind of look at the movement of the block and the ramp as movement of one rigid body at that one particular moment in time. So in some sense, it looks like this small mass m is stuck to the ramp. So you can treat this almost like completely inelastic collision. I mean, it's not, energy is still conserved and we're gonna be using that. But you can treat it like a completely inelastic collision to say, all right, it's moving together. It's as if it's stuck. So we can use conservation of momentum to try to figure out this final velocity here. Now, the way the question is asked, you don't stop there because it's not asking for this final velocity here. It is asking for this height. So after having found this v, you can then use, oh, well, energy is still conserved. So in a completely inelastic collision, that reduced kinetic energy will just have disappeared into thermal energy or whatever. But in this setup, that kinetic energy didn't disappear. The kinetic energy turned into gravitational potential energy. So for the second part, you say, all right, use conservation of energy. And say, my initial energy, which would be just the initial kinetic energy, is equal to the final gravitational potential energy. And then this is the part I see students who are able to visualize forget about. There is a final kinetic energy because the ramp and the block are moving together. And that's the part you need to get in order to be able to get full credit on this part. So once you realize these key facts, then the rest of the math is pretty easy. That's kind of one of the reasons we really recommend that you learn how to use conservation law strategies, because it'll help you solve problems more easily. But you do have to visualize the setup and think through to be able to do, I mean, this is what I keep saying. You need to be able to identify conserved quantities. And there might be some other constraints, like what we realized about these two things moving together at the same speed. And that there isn't like one single rule that I can give you that'll cover many situations. This is where your physical intuition and visualization skill really comes into play. Okay, so that's part A. I won't work it out. You can work it out, look at the detailed answer. It says, after reaching the maximum height, the block slides down and moves to the left with the speed of v1. Oh, so it's describing this setup where, so block M slides down the ramp. And what it ought to mean is it completely finishes the sliding down the ramp. So at the setup when this problem is describing, a block has slid down and now it's moving to left with the speed of v1. And it's telling me that the ramp is continuing to move to right with the speed of v2. So it says set up, but do not solve the equations necessary for solving for these two speeds. So, so you should do that first step, identify conserved quantities. And hopefully here you realize that one, momentum is conserved. There are no net external force that's departing net impulse over the duration of time. It gets a little bit complicated, by the way, while the mass is on the ramp, because then there's actually upward and downward momentum. That's one of the reasons I don't ask those particular questions. I ask you after it's finished sliding down. So there's one, momentum is conserved. And two, this is a bit of a unique setup where there's no friction anywhere. There's no reason for energy to change. Normal force does change energy of individual constituents, but since the normal force is between the two objects, all it should end up doing is just transferring energy back and forth between these two objects. So energy is conserved. So you write down conservation law equations involving those two things. Write down conservation of momentum equation, which will look like the total initial momentum is equal to the total final momentum. And I like to write this in a way that it starts all the way from the beginning to the end, because I could have made a mistake in the intermediate step in part A, and I don't want the answer here to be affected. So my initial momentum actually refers to the momentum when the block was moving to right at speed of v0, and the ramp was moving. And the final momentum. So I'm going to put the signs in, or the directions into the signs in my equation. So the small mass m, it's moving to left. So I will say it's moving with the momentum minus mv1 plus the ramp is moving to right with the momentum big M v2. So this is one equation. And as you look at this, I hope you realize that you don't have enough equations to solve this particular setup. You have v1 and v2, both are unknown, but you have only one equation. And this is where conservation of momentum or conservation of energy becomes necessary to solve this part of the question. And this is going to be a common feature, by the way. When you have conservation of momentum alone, it's usually not enough to work out all the details of the collision. You need to be usually told one additional fact. And that one additional fact can take many different forms. If you are told it's a completely inelastic collision, then you are being given the relationship between these two final speeds. So that could be your one additional fact. Or you could be told one of these two velocities. That would be one additional fact. Or finally, you could be told or given enough information to figure out that it's an elastic collision, that energy is conserved. So that could be one additional fact. All these have one thing in common, is that conservation of momentum completely by itself doesn't actually tell you how, give you enough information to work out the interactions. So then I need to write down the conservation of energy equation. So conservation of energy, I guess here I don't need to involve potential energy, because especially if I'm starting from the initial kinetic energy, where the only thing that was there was the kinetic energy of the block, 1/2 mv0 squared, no potential energy. And in the final state too, there is no change in potential energy. The blocks have come apart. They're at the same height that they were before. So I can just say the total final kinetic energy. So 1/2 mv0 squared is equal to 1/2 small m v1 squared plus 1/2 big M v2 squared. I guess if except that the question specifically tells me to do this without solving these equations. But show that it's possible. So what I would point out is I have two unknowns, which are v1 and v2, and two equations. So I should be able to solve for the two unknowns. That's kind of all I need to do. Count the number of equations and unknowns, and that should be enough information to tell me if it's solvable. And then it says without solving the equation. So all right, will leave it not solved. I think if you go to part C, that's where, I tell you to, okay, solve the equations. There's two reasons for that. One is I do believe it's important that people are able to set this up. That setting up your system of equations, that's really the more important step. Doing the algebra here, computer algebra system can do that for you. But a human being needs to set up the equations that the computer algebra system can solve. So, you need to know the how to set it up, that's the more important part. And now, I guess for this question, I felt like you have enough time to do the algebra. It can get complicated. These squares do kind of give you trouble from time to time. So, you know, when you're in the exam and if you see a question like this, make sure you won't waste too much time. But this algebra is doable. It is doable. So I'll leave that for you to do. Part D says your resultancy should show that in the limit began the ramp barely moves at all, the larger mass and the carry if big M equals calculate what fraction of the unit again. Now, if you did the parsing completely correctly, then great. You have all the formula you need, and you can simply plug in this. So let me show you one of the useful test-taking strategy, test-taking skill to develop is how to continue answering the multiple part questions, especially when you weren't able to get an answer to the previous part. So let me show that. Now, I think I'm still assuming that you were able to get part B and that you did write down these equations. Then what I'm going to do is I'm going to plug in the numbers given because what makes that particular equation challenging is that you need to work it out algebraically. But if you are able to kind of plug in this number here, then there's a chance, hope, that it might work out to be simpler, much simpler. So let me write this down. The first equation is conservation of momentum, mv naught. Is equal to minus mv1 plus big M v2. And the second equation was conservation of energy. 1/2 mv naught is equal to 1/2 mv1 squared plus 1/2 big M v2 squared. And there are some things actually you can get rid of right away. This 1/2, you can cancel it out from all the terms. And it would have been nice to be able to just cancel out the m's, but because of this different big M, you can't. This is where the number given here comes in useful. I can plug in, let's just plug in what that big M is. So plugging in that value of big M, it's 10M. Now, when you do this, you lose the generality of the formula. So if we had other choice, we wouldn't do this, but I'm pretending that I didn't get the answer to part C. So I'm trying to figure out, all right, how can I answer part D still if I don't have part C right? One of the things I can do is, all right, plug in the given number, the 10 times the small m for the big M. So when you do that, then you should be able to see that you can, now I can cancel out all the m's. So m's are all gone. Then what I end up with is v naught is equal to minus v1 plus v, be careful here, plus 10 v2. And this one becomes v naught, I forgot the squared. V naught squared is equal to v1 squared plus 10 v2 squared. So you still have two equations, two unknowns, so you shouldn't be able to solve it. Now, I guess what I'm trying to say is, if one of the reasons you couldn't finish part C was that there was just too much algebra with all those symbols, then what I did in part D with this additional information given is come up with a system of equations that is a bit simpler. So you might be able to do this numerically. You might be able to, or I guess the first thing I would do is I would just eliminate V1 by adding them together. But wait, well, no, the square does make it complicated. So there's still quite a bit of algebraic work to do, but plugging in the given number at least lets you deal with fewer symbols.